So welcome back again to Benelli's Academy. Because of this video, we'll be talking on the tray design. Now, I said earlier that under gas dispatch operation, gas liquid dispatch operation, you have the disperser, you have the agitated vessel, you have the tray design. So now, and I explained disperser, instruments, agitated vessel, the mechanical vessel that so you understand. So now let's go back to tray design. We all know, believe from distillation, everybody say something that they have one diagram like this. Your distillation column, we believe that I say material balance, energy balance. You have something like this. You have something like this. I think there is this heat here. This one. You have reflux. You have distillate. You have bottom. You have feed. So and you call this place your tray, right? This is what you are calling tray in your own diagram. But getting to the industry, the tray is not in this way. The tray is in cylindrical form, like this. So you have many layers, but there's something that's happening in this case. So above the feed, we are having enriching, and below the feed, you are having stripping. So just note that. They can ask you to draw those things. So check your manual, you're going to see all those things there. Another thing there is that now in this tray design, we have hose. Inside this tray, on our own diagram, same thing with this. You have hose, you have hose, you have hose, you have hose. Now, and this is how this process is being is happening. So under that, they ask this question: what is flooding and this thing? No, you have flooding. Yeah, we have flooding. You have stripping. No, you have flooding and one other thing like that. So flooding or whelming or something like that, dropping or something. So whipping. So now, if you know this liquid is leaving from here, big gas. I think gas in, liquid in. You understand? So and gas out here. Now you know if the water, the liquid is coming from up. So you are going to drop in this tray. Are you getting this? After you now drop on the tray, the gas here is the one that's telling the process that are going to happen in this case. Maybe the water is going to whip or drop or flood. Now, what causes flooding is when you have the high pressure or the rate of this gas. Now, I'm going to fall in the page. If this thing wants to happen, the gas that's coming from up and the liquid coming from gas coming from down and liquid from up, getting to that tray, that's where the process on the tray they have a equilibrium state. It should be in equilibrium. At any tray there's equilibrium. But some cases, if the heat, like the pressure acting on that this thing is more, so the water is not going to able to draw to perform an equilibrium state. So the water is now going to pass through this place, Mawa to the other tray. I getting this? You now come to that state. That's what we call flooding. But situation whereby you now have a low flow or gas, like a low pressure. So this place, instead of it to be in equilibrium, to the water will now be dropping from here because of the low distance. It will now be dropping under the O. So that's what we call whipping. Are you getting this now? So under this tray, we have a downcomer area, which is this line, downcomer area, and we have the tray space or hose space, something like that too. So in this case now, what you just want to talk about is that how to design a tray too. You can check your manual, what you have to know before you design a tray, the flows, everything, the downcomer area. So we now have some formula before you can design a tray. The formula to use, you have what? The flooding area, which is what? AF is equal to what? Q, that's like volumetric flow or flooding. I just want to say like volumetric flow rate. Everybody knows volumetric flow rate as Q. But I just want to specify it because we are dealing with flooding, right? And we have what? VF, which is what? Our flooding velocity. Are you getting that now? Which is still the same from continuity equation. Which is that what? Q is equal to what? VA. What do you have? Just make it the formula. Get your area of flooding. You understand like that? So now the next thing is that to now calculate flooding velocity now, which is VF, we have the formula that lead them together, which says that CF is equal to what? Rho L minus rho G over what? Rho G raised to power 0.5. That's that. And after that, to now calculate, do you know what's funny about this case is that you have to get one before you get another one. For us to get VF, we have this formula. For us to now get this formula, we still need CF formula. CF formula says alpha log 1 over tau tower diameter plus beta sigma. This is surface tension. Surface tension. Surface tension. This divided by 0.02. This by 0.2. So which means before you can get your VF, you must get this. And tower diameter, which is the same thing as L prime, G prime, rho G, rho L, this by 0.5, which is equal to this. This is the formula for tower diameter, but this is sign for tower diameter. Are you getting this? Yes? Which was, yeah, volumetric flow rate. This place is not mass flow rate. So even if you are giving the mass flow rate, you have to convert it to volumetric flow rate. You understand, like that? So now, that's another thing. So this is our Q. So this is our tower diameter. This is what? QL, rho G, rho QL, QG, rho L, rho G. This was 0.5. So if you now put this to this, our tower diameter here. So you have alpha log 1 over this thing, because that's our what? Our tower diameter plus beta sigma, this thing, everything. Just our CF back. And that's to calculate the what? The this is flooding coefficient. Yeah. Flooding coefficient. Flooding coefficient. So after that, we have area total area, which is what? Area of flooding minus over 1 minus downcomer area. So sometimes I'm going to give you the downcomer area. So there's formula for alpha in your manual, but in some cases they are going to give you the formula. They may change the formula, but if on normal basis they are not giving any formula for alpha, you just use the constant alpha from your manual. So that's page 30 something. So check that. But because we want to solve fast question and we are giving alpha, that's why I don't need to write it here again. So now another thing we have what? Our downcomer area, total downcomer area. The reason why is this is that when you are given some question, they will not give you the total velocity, which means they can tell you that this, assuming you are giving normal velocity, your total, maybe you are giving at 100 saturated velocity, right? Maybe you have 100% saturated this thing, which means you don't need to find your downcomer area again. The downcomer area you get from there is going to be your normal downcomer area. But some cases they can give you at 0.7%. Are you getting it? Which means you don't have pure this thing. So you have to now calculate the okay, now so let's talk about the past question now. So I said the correcting factor here is what? 22.4, and the formula to calculate the average to calculate the density of gas, the average molecular mass of this thing. So now let's go to the question. It says that a stream of, so they said steam is used in stripping diluted aqueous solution methanol using sieve tray. So this is the tray that I want to use to strip out the methanol, and liquid the stream flows at 0.1 kilomole per second. This steam. So, and as I said earlier that the gas is entering, right? So let's say this is steam. This is what? The liquid, right? So this one is entering this way. So the steam is going the steam flows. So let's say the flow rate of what? Of gas is equal to what? 0.1 kilomole per second, right? Or the steam flow rate here is what? 0.1 kilomole per second. So we have another thing. It said and the methanol concentration is 15%, while the aqueous solution contains 15% mass fraction of methanol flows at 0.25. Now, what they are trying to say is that here is that at the steam, because they are still talking about the steam, they said we have what? 15% of what? Of methanol. So in this case, we have what? 50% of what? Methanol, which is what? CH what? CH3OH, Abi? So now, if you have 50% of methanol, back to our material balance, the 95% is going to be for what? 85% is going to be what? You got H2O, or you have here 0.15, and here you have 0.85, right? So now, the second one too, they said we have 15% mass fraction. Please look at that. They said what? Mass fraction. So in this liquid stream, you have 15% mass fraction of what? Of methanol, CH3OH, right? So, and we have the 85%, right? H2O. So now, and they say the mass flow rate of this liquid phase is now what? M flow rate of this is what? 0.25 25 what? 25 kilomole per second. So the mass flow rate of liquid will now be what? 0.25 kilomole per what? Per second. So now they said the operation is at 90%. Hello, the operation is at 90% and 1 atmospheric pressure. So you have the T1 is equal to what? 273, and our T2 is what? 90 plus 273, which is equal to what? 90 plus 273. So we have P is equal to what? 3 what? 3 Kelvin, right? Kelvin, we have 1 ATM or 101.32 kilonewton per meter square. So the density of the solution is 961. So they gave us the density. Hello, the density of what? Of the solution. The density of liquid is what? 961 kilogram per what? Meter cube. Now they now said the spacing tray is 0.7 meter. So this T is what? For spacing tray. Maybe you should write it like this. 0.7 meter for what? Spacing. Hello, please. Hello, please. If you want to go for class, go for the class. So we have what? 0.7 meter for the spacing tray, right? So now they now said diameter of perforation. So we can say the space of this tray 0.5, 0.7, and the perforation. So we have the pitch perforation. Pitch perforation is equal to 0.012 meter, and the downcomer area is equal to what? Downcomer area is equal to what? 9%. 9%. Now of the whole area. So now they are now talking that it's 9% of the whole area, which means it's not 100%. It's 9% of 100. Are you getting it like that? So they continue with this. They said the wear length. The wear length is always this is the downcomer area. We have the wear length. The wear is always in that tray. Like if you check your diagram, I'm going to say. So the wear, yeah, the wear length is what? Is 0.55 d, right? So and the flooding velocity. So they gave us BF, which is what? 80%, right? 80%, right? Determine now. Did I say you should calculate the what? The area of flooding. You calculate the total area. You calculate the diameter of. Giving. They still gave us another thing. They gave us alpha is equal to 0.030 T plus 0.015. No, our beta. This is beta. And our alpha is equal to 0.0744 T plus 0.01173. They gave us the surface tension sigma is equal to what? 0.040. So, and diameter of perforation is 5 millimeter. Pitch perforation is 0.12. So calculate this. So now we are given most thing we need for this solution. Now they now ask us to calculate what? The first one, you should calculate the area of flooding. Now before, look, let's go back to this formula. If we want to calculate area of flooding, we need volumetric flow rate and the velocity of flooding. To calculate velocity of flooding, we need CF. CF, we have a formula. So from this now relate us to alpha and beta. So we need to first find our alpha and beta in normal way, because they are giving alpha is not in the right way now. So we have to convert our alpha, where this T is our space, tray space. You have tray spacing. Now, another thing is that for us to now calculate our we need the density of gas too, because we have to apply it to the formula here, LOG, to calculate our tower diameter. So we need this, we need flow rate of L, we need QG also. And before that also we need to calculate PG now is this formula. So we need the average molecular weight of what? Of gas. Are you getting it? And correction factor. So let's start from solution. Let me remove this part. So I'm going to call this two formula for me. The average molecular weight and density of gas. So now, solution. So let's find our alpha. Our alpha is equal to what? 0.0744 is bracket. What's our T? 0.7 plus 0.01173. What's going to be alpha? So our beta also is going to be what? 0.030 bracket 0.7 plus 0.015, which is equal to this. So we're going to get our alpha and beta in that case. What? Which alpha, right, is what? 6.3. So all that going to be our beta. You can find that one too. Now, so after you now get our alpha, we need our average molecular weight, because if you want to calculate the volumetric flow rate of liquid, you need average molecular weight, and volumetric flow rate of gas, you need T1. You have gotten T1 and T2. So now we need to calculate beta is what? What? 0.06. No. 0.0036. So this one is 0. This. So the first one to calculate is what? Calculate the average molecular weight of what? Let's start with what? With gas. And I gave you a formula for average molecular weight of gas. So the average molecular weight of gas in this case is now going to be, let me erase this. So we go from mass, which is what? For mole. Mole is equal to what? Mass over what? Molar mass. Which means our mass, because mass is also weight, is equal to what? Mole times what? Molar mass. Are you getting it? And the gas given to us here is what? Is what? Methanol, which is what? CH3OH, which is equal to what? You have carbon is what? 12, Abi? 12 times 3 plus 3 plus 16 plus 1, which is equal to what? 32. What? In what? Kilomole, right? Kilomole. So now we are getting our what? Our molar mass. Molar mass of what? Of gas. So now calculate our average molecular weight. So average molecular weight here will now be equal to average molecular weight of gas. Will now be equal to what is, because they gave us two gas here, we need to calculate the average molar mass of H2O2. So molar mass of water H2O will now be equal to what? 2 plus what? 16, which equals what? 18 kilomole, right? So average molecular mass of gas will now be what? The mass, the mole. The mole of this is what? 0.15, right? 0.15 into bracket. What is the molar mass of what? Of CH3OH? We have what? 32. Plus, you have the second one. What is the mole of the second one? You have what? 0.85. 0.85. What is the molar mass? Is what? 18. So our average molecular weight of gas now be equal to what? So if you multiply that together, you are going to have 20.1. So you have 20.1 kilomole, right? Is it kilomole? Yes. So kilomole. No, that is the what? Average molecular, it should be gas now. Kilomole, yeah. But this mass over molar mass should be what? Kg per what? Kilomole per what? It should not be coulomb per kg. I guess that. So now let's continue. You know this. So the next one is what? Let's calculate the average molecular weight of liquid. Calculate average molecular weight of what? of liquid. And I gave you a formula for average molecular weight of liquid. I said what is equal to what? Average molecular weight of liquid. Check your notes. You said what?
Total mass.
Total mass. Total mass of liquid over mass over molar mass mm plus mass over molar mass of B. So like A and B now. So our average molecular weight of liquid will now, because what's our total mass? The total mass, because from the question they said we are giving a mass, not a mole. They say mass fraction, which means you are dealing with mass here, not mole. So you're going to be 18 plus here, you have what? 100. Are you getting this like that? So your total mass here is going to be what? 100 over your mass of the first one. This is mass of your CH3OH. You have what? 15 over what's the molar mass of gas? The molar mass of this one is what? 32 plus Abi. We have mass of the second one is what? 85 divided by what? 18. So our average molecular weight of liquid will now be equal to what? Compare that in your calculator. You have your answer. Let me open the question. So now, what's our average molecular weight of liquid? Is what? So you can press that in your calculator and have our answer. So, but note that from the question they asked us to calculate what? The total, area of flooding velocity, which is our AF. I getting that? But we need to calculate is what? 19.26 kilomole. So that's that on that. So the next thing for us to calculate, you have gotten that. So we can get our density too, because you need the average, you need the volumetric flow rate in this case to calculate the what? Tower diameter, because we need CF to get AF. You are looking for area of flooding. You need QF or QG. So we are not giving QG, but you can record that, because you have to calculate. And if you record from this, let me remember this part. You are giving mass flow rate. So we need record from continuous equation. It says that Q is equal to what? BA. So QG, and we are giving, and QG is now what? Mass flow rate over what? Over density. Are you getting it? You want to calculate for mass flow rate when we are